right. Hi, everybody. I'm François, and this is Stefan. And so we'll be presenting you a workshop about teaching machines to read and hopefully understand what they're reading, for at least some definition of understanding. And the definition of understanding we will be using is the ability to answer reading comprehension questions, which might not be the best definition from a philosophical standpoint, but it's a practical definition, and we're here to solve a problem and not do philosophy. Okay, so it seems like a pretty complicated problem, teaching a machine to read something and then answer a question about what we just read. But we got the right tool for the job, and that tool is not Excel, thank God. I don't recommend you try this in Excel. So we're going to be using Keras. So just to get a feel for the room, has anybody used Keras before? Okay, so that's quite a bit of people, maybe 20%, 30%-ish. Anybody used Ciano before? Roughly the same. Torch 7? Few people. Okay. Anybody has actually used neural networks or deep learning, in code before? Okay, that's not too much. So hopefully, by the time this workshop is over, you will have a better familiarity with how to go about implementing your own deep learning algorithms. Okay, so if you want to solve a problem like teaching machines to read, first you need to define exactly what success means. So you need a task and a metrics of success, kind of a benchmark. And up until very recently, there was no data set or no benchmark available for machine reading. And it's only in 2015 that we started seeing examples of that. So in February 2015, Facebook released the first data set for natural language question, reading comprehension question answering, which was called the BABI data set, BABI. And today we also have a second data set developed by DeepMind, based on newspaper articles. And so today we'll be using the Facebook dataset. And so it's a synthetic dataset, which means that the data, the sentences and questions were generated by an algorithm. So it makes it very clean, but also potentially flawed in some ways. And so there are 20 tasks. Each task is focusing on one specific cognitive ability, like things like temporal reasoning or fact chaining, deduction, induction. And so this is, I hope it's readable. This is an example of one task. So basically, you have a few sentences about people doing something with objects in places, like describing a situation, basically. Then you have one question, and the answer to that question is going to be one single specific word that's found somewhere in the input sentences. So the input text and the question as the inputs to the system. And then the system is going to come up with this one word. So that's the situation. That's the positional problem. So if you want to learn more about the BABI dataset, you can check out the website. You can also read these two papers. So this first paper introducing the dataset, and this is the second paper introducing memory networks, which are state-of-the-art architecture for solving this type of problem. It's one of two approaches that we're going to be implementing today. All right, so we don't have much time. I'll try not to take more than 1 hour. So we're going to try two approaches on this problem. So first is kind of the naive approach, which is just using an LSTM network, which is a specific type of recurrent neural network, to solve the problem. It's not going to work very well, but it's going to kind of work, so that's already something. And then we're going to implement Facebook's solution, which pretty much solves the problem. At least on this data set. It doesn't mean that Facebook has found a solution to teaching machines to understand any text, but it found a solution to this specific task on this specific data set. And so because we're using Keras, it's going to be pretty simple. So the first approach is going to take about 10 lines of Keras, and the second one, so which is a state-of-the-art algorithm I published very recently, it's less than 20 lines. So before we actually dive into the code, I'd like to introduce a few high-level pointers about how to deal with text and using recurrent neural networks. So anybody used recurrent neural networks before? Okay, very few people, less than 10. Well, that's a great place to start, right? So one pattern that you will find everywhere in modern natural language processing is to encode sentences, or more generally sequences. So it could be sequences of words or sequences of characters. You encode them into dense vectors. So a vector is just a series of numbers, basically. And the way you do that is first you break up your sentence into atoms, which could be words, which could be characters. To each atom, you're going to associate one index. So one integer. It's basically like a mapping between words and entries in a dictionary. Then to each index, you're going to associate a dense vector, which is called the embedding step. And after this embedding step, you're left with a series of a sequence of dense vectors of the same length as your initial sentence, right? And then when you feed this, sequence into a recurrent neural network, and you look at the last output step of the recurrent neural network, you're going to get, one single vector that's encoding information about the entire sentence, about the order of the words, about what the words were, and so on. So, and if you train this setup, so the recurrent neural network and the embedding, if you train it end-to-end with the right loss function, this final output is going to encode everything you need to know about the sentence. And also one thing that's commonly done in natural language processing is a reverse operation to this, which is starting from such a vector that encodes information about a sentence, doing the reverse, so generating a sentence. And for instance, very recently, Google launched this feature, auto-replying to your emails. That was pretty cool. So it's using exactly this setup. It's encoding your email via an embedding and a stack of LSTM units, which is a type of recurrent neural network. So it's encoding your emails into a dense vector. And it's using this dense vector to generate an answer using the inverse setup. OK. So in our case, we will just follow this pattern. We are not going to look at actually generating text, because we only need to output back one word. So since you don't seem familiar with recurrent neural networks, here's a very, very quick high-level overview. So it's obviously not enough to understand what they are and what they do. So you should really do some research about that when this is over. It's a very cool topic. But the very high-level idea is that it's a machine learning algorithm that looks at a sequence of time steps, a sequence of inputs, and over time it's going to build a memory of what was found in the sequence. And at a given time step, it's going to look at the memory, it's going to look at the current time step, and based on both these data points, it's going to output something. So clearly, it's going to output something new at every time step. And if you let it run to the end of your input sequence, and you only look at the last time step, at the last output, this output is going to encode information about the entire sequence. So that's a very basic idea, but it's a very powerful idea. Within this idea, you have everything you need to solve natural language processing problems. So the simplest thing you could do to solve the problem of answering the baby questions is something like this. So a neural network with two branches. First, you're going to take the input text. You run it through an embedding. You run it through a recurrent neural network. You get a vector out of that. Then you take the question. You do the same process. You concatenate these two vectors. So the vector that contains information about the input and the vector that contains information about the question. You concatenate them, and then you run a logistic regression on top of that. So taking as input these concatenated vectors of meaning, and as output, you do basically softmax over all possible words in your dictionary. And the top scoring word is going to be the answer to the combination of the input and the question. And so this is a setup that's differentiable, so trainable end-to-end by backpropagation, which means that you can just show this setup examples, so show them properly answered questions, and it's going to internally build a model of how to answer new questions. All right, so using Keras, this is only 10 lines. It looks like this. It's essentially a very straightforward way of putting this little diagram into code. You set up an embedding layer, you add a recurrent unit. So this is for the input. You do the same for the question. Again, just 3 lines. You concatenate the two with a merge layer. So taking the input encoder, the question encoder, and you run a logistic regression on top. So logistic regression is just going to be a fully connected layer or a dense layer and the softmax. And once you have that, you can compile the model, train the model on known examples, and it solves the problem, pretty well. Not like perfectly, but pretty well. So because the majority of you, roughly 60, 70%, don't know about Keras, here's a quick intro. So it's deep learning framework for building algorithms. So it's in Python. It's built on top of Cyano. Cyano is a tensor computation library. So basically, it's a way to compile your Python code to code that's going to run very efficiently on CPU and GPU. So using Keras, everything about Keras really focuses on simplicity. So for instance, we separate topology from optimization. So the way you define your network architecture is completely separate from the way you train it. And this modularity is very good because it means that once you've defined a network, you can try to train it with different strategies. Like maybe you can use Allegrad, like we saw before. Or maybe you can just use classical stochastic Gaussian descent or something else. Maybe you can even implement your own optimizer. All right. So let's dive into the code. So there's a GitHub repo you can clone. And you're going to have Keras installed and Cyano installed. So I believe Arshak prepared AMI on EC2 with everything you're going to need already installed. So maybe you can use that. I'm not sure exactly how it's going to work. Do you have access to the AMI? OK, cool. So if you just log into your AMI, you're going to want to clone the repo. If there's already a folder by this name on your AMI, just nuke it because we made some changes, so you're not going to be able to update it. So just RMR, that folder, clone the repo. You don't actually need to do these 2 steps because I believe Arshak updated the AMI. OK, so these 2 steps, you don't need to do it. Just clone the repo. Yeah. Sure. Yeah, I would recommend, so we made some changes, so I would recommend actually deleting that directory and recloning it. So in that repo, you can find 3 files. So you have one utilities file that we're going to use to download the data. So it's already cached on your AMI normally, so it's not actually download anything. So download the data, parse the data, and vectorize the data. And then you have 2 scripts that implement, so the first model that we just saw, and then the memory network. So do you want to walk through the utilities? Yeah. And you can present the first grade, like, because you did the benchmark and everything, so you'll be better able to explain. Well, just present whatever you want, and then I'll take over. So everybody got the files? Everybody? Okay. Looks like we're good. So you have 3 files, right? You have the utilities, workshop utils.py, LSTMQA, which is this first approach to the code we just saw here, and the memory network. So first, Stefan's going to introduce basically the way we go from raw sentences to tensors that we're going to be able to process with Keras.
First, computing and data science.
Oh, thanks.
So as with most data science, unfortunately about 70–90% of the time is spent dealing with the data itself, munging it, pre-processing it, so on. And it's the exact same story here, even though it's an incredibly simple data set compared to, say, other ones such as visual information or whatever else. So the first thing that we end up doing is Keras actually provides us a utility that will actually go ahead, grab a file at a URL, cache it locally, and you can then just grab it later on. You don't need to re-download it, which is a really nice thing, for example, if you're dealing with, say, a larger data set. So the second thing is, once we've actually got the path of the file, we just go ahead and open it, pull out the data set itself, which it's composed of a huge number of different examples, I think 20 tasks in total. And each task has either 1,000 questions as training or 10,000 questions as training, and then a test file of 1,000 questions each. So in this situation, we're, I think, by default looking at single supporting facts. So we're going to be training over 10,000 of these different examples. And the reason that we've just got this is that it's basically a single supporting fact, and then there's a train and test split. So we've actually written functions that kind of help you out in actually getting these stories across. And these are contained in workshop utils. So if we jump over to workshop utils and jump down to the bottom, so we have get stories, which literally just pauses the file. It walks through the text. It knows whether it's a sentence that's supporting that, Stephen picked up the laptop, Stephen walked to another room, Stephen put down the laptop. And also whether or not there's a question associated. So at some point it might ask, where is the laptop now? And it would say, the living room or something like that. So this code just pulls that out and gives you the data set back, which is then composed of 3 different parts. So it's the sentences themselves, supporting facts if your machine learning algorithm needs them. So specifically, which sentences actually lead you to the correct answer, and also the answer itself. So once we've actually got the stories in place, we've only just got a whole bunch of individual words as text, tokenized, so split. So you have a huge list of just individual words. Now the thing is, we need to push this into a vector format of some kind. You could, for example, if you were doing a different task, it might be a good idea to initialize from something like word2vec, which has kind of good, I guess, world knowledge about what these words are and how they might be related. But for this task, it's actually far simpler. The vocabulary is tiny, and kind of the similarities between words are really quite minimal. So we're just instead going to learn an embedding from this data itself. So this line, horribly long, sorry, I shouldn't have written it like that, but all it does is grab the vocabulary, which ends up being, I think, between 20 and 30 words max. So each of these words is the entirety of all the words that occur in our data set. And so we end up basically assigning each and every one of those words a number from 1 to n. We leave 0 spare because 0 is going to be like our padding sequence. I'll get to that in a second. So once we've actually got this, we can then throw into the vectorized stories function all of the text. So the train stories, our connection between a given word and the given number that we've assigned to it. and also the maximum length that we actually want our vectors to end up being that represent all of these different words. So in vectorized stories, we end up creating 3 different partitions. So one is X, which is just the stories themselves. Another is XQ, which is the actual query that we're asking. So we separate those 2 out as shown in the diagram before. And Y is just the answer that we're looking for at the very end. And for each of the kind of story, query, answer tuples, we end up going through and just listing out the integer that's associated with each word. So if we end up with like, the cat and dog, it would end up being like 1, 3, 2, 1 or something like that. And we do that for each of these. And for Y, we don't need to do it as a vector because it's just going to be a single output at the end, as François said. So we then just assign the kind of index itself. So again, the word is given an integer. We set that 1 single bit in the output vector to on, and a similar sort of thing, except for the rest of them. And finally, the pad sequences function is a helper written for Keras, because if we have, say, 100 different stories and they're all of different lengths, one of the issues is that you can't actually make kind of a good generic function that can, say, do a batch computation over 32 of them all at the same time. So instead, we pad any of the shorter ones to the maximum length that we might end up seeing, so we can apply one giant kind of optimized function to that data. And that improves kind of the number of different others like that as well. So that's basically all that's required to get this data into a format with vectors that you can then throw straight to the machine learning algorithm. I might throw it over to François.
Okay, thank you. All right, so let's take a look. So at this point, after you've run these utilities, you have as input so 2 sets of data. You have the training data and the test data. So the test data will be used to evaluate how good you are at answering new questions. And the training data is the set of examples you're going to show to your network to teach it to recognize patterns useful for answering questions. Okay, so we added some lines to print useful information about what this input data contains. So in particular, the shape. So I don't know if you're familiar with tensor libraries such as NumPy. Okay, a little bit maybe. Ciano. Basically, the shape. I don't know if you've seen a matrix before, but it has a certain number of rows and columns, so that's the shape in our case. And tensors are just a generalization of matrices in more dimensions. Okay. All right. So now building the actual learning model. So you start with an object called sequential. So a sequential object, it's basically a container for layers. So you're going to instantiate this sequential, and then you're going to add a stack of layers on top of it, right? Okay, so for instance, if you look back at your diagram, you can see here you've got some kind of sequence, here you've got some kind of sequence, and here too. And the way you're going to do it is you instantiate 3 sequential containers. And to the first 2, you're going to add an embedding layer, a recurrent layer. Second one, same thing. And the last one, you add 2 layers that will implement a logistic regression. So it's very straightforward in Keras. Embedding is called embedding. You just specify the input dimension, which is the size of your vocabulary, so the number of words in your vocabulary. And the output dimension is going to be the size of the space on which you're going to project this vocabulary. So the output of an embedding is a sequence of dense vectors, and these dense vectors are going to be, in our case, 64 dimensional. So then you add a recurrent layer. So in our case, we're going to use LSTM, which is a very popular type of recurrent neural network So it comes with Keras, so you don't really have to do anything. You just specify that you want it to output vectors that are 64-dimensional. And we specify return sequences equals false. So that means that this recurrent unit is only going to output the last, the output of the last time step. So as we saw, a recurrent neural network is going to actually predict a sequence of outputs at the same length as the sequence of inputs it's seeing. In our case, so each input is a word, or as a vector encoding a word. And we are only going to keep the last output, which is going to encode information about the entire sentence. So the reason we do this is because we want to go from a sequence of vectors to one single vector. So you do the exact same process for encoding the question. And what you get back is, again, a single vector containing a geometric representation of the question. Then you merge the two. So the way you do it, you instantiate a new sequential container, and you add a merge layer. So a merge layer is a way to take two branches, or more even, so an arbitrary number of branches, and merge them. And you can merge them in different ways. You could sum them, you could concatenate them on a specific axis. So in our case, the last axis, which is -1. So in Python, you can index arrays with negative values. So -1 just means the last element in a list or array. So the last axis in our case. So, okay, and after this merge, so you're concatenating two vectors of size 64. So the output is going to be one vector of size 128. And as you can notice, Keras does automatic shape inference. So when you're adding a new layer, you do not need to provide Keras with information about the shape of the input. You only do this actually in the first layer of a branch. So for instance, in our case, you do it for the embedding layers. But for any subsequent layer, Keras is just going to infer the size of the input by looking at the previous layer. So as you would expect it to do. So logistic regression is just one fully connected layer, and you want it to output vectors of the same size vocabulary. And then you're going to run softmax on these vectors. So softmax is a way to turn an array of scores, a vector of scores, into a vector of probabilities, a probability distribution. So the output of this is a probability distribution over what? Over your vocabulary, right? And the one element in the vocabulary that has the highest probability is going to be the answer given by this network to the combination of the input and the question. Okay, so that's a lot to go over, I think. So any questions so far? Yes? Yes, so in our case, Keras is going to learn the embeddings jointly with the task. So we don't use, so one possibility would be to use pre-trained embeddings, things like word2vec. If you were to do this, you would add some arguments to the embedding layers, specifying the embedding metrics you want to use. In our case, we don't specify anything, which means that the initial embeddings are going to be random. And so the weights of these embeddings, the content, is going to be learned jointly at this step, when you're applying your optimizer, which in our case is an optimizer called Adam. So when you're applying this optimizer, it's going to start learning the weights and the embeddings. Any other question? Yes? Which output? I'm not sure what you mean, but we can try actually running this script, right? And it's going to output all our little print lines. So right now it's compiling, right? Compilation is going to take like roughly 1 minute. So some information. So in the vocabulary, we have 22 unique words. The longest story is only 68 words. The longest question is only 4 words. That's pretty small. You have 10,000 questions, well, combination of inputs and questions and answers as training examples. And then you're going to evaluate how well you're doing on new questions, on just 1,000 new questions. So before the embedding step, that's what an input looks like. So first, you have a list of word tokens. So that's the input text. Then you have the same for the question. And then you have one single word that's the answer to the question. OK, so after the vectorization steps, which is what Stefan walks you through, what you get is that you replace that. OK, so it started training. So it took less than a minute. So you replace these two lists with tensors. So the size of the tensor is going to be 10,000. That's the number of examples by 68, which is the length of the examples. And so 68 in our case is the longest example. And you know, all the examples that were shorter than that are going to be padded with zeros to match this length of 68. OK, do you do the same for quick? Yes?
There's an example.
It's part of the Keras repo. It's not part of the workshop. Yeah. Yeah, you can use that. OK. Can you show me?
Here's Keras.
Yep.
Fine.
It's not part of Keras. So
it's not called Keras. I don't know what that actually means.
So take a look at Keras workshop.
The Keras workshop.
Yes.
Thank you.
All right. So yes. So the model is currently training. So it's training on CPU on my laptop right now. Each epoch is taking about 22 seconds. So that's pretty fast. And you're printing a number of metrics that you want to monitor during training. So you're printing the loss function. So in our case, what was the loss function? So at this step, at the compilation step, you are specifying the loss function you want to optimize for. And you are specifying the optimizer, which is kind of the optimization strategy you're going to use to get the lowest possible loss function. So in our case, it's categorical cross-entropy, which is what you want if you want to implement heuristic regression. And Adam is kind of arbitrary in our case. We could replace it with SGD at a grad, RMS prop, anything really. It doesn't really matter in our case. OK, and another thing you want to print out is the accuracy you're getting on the training examples and the accuracy you're getting on the validation examples. So as you can see, we can answer a bit over half the examples correctly currently, which is pretty good. It doesn't solve the problem perfectly, but it's pretty good. And roughly the same for validation accuracy, which means that the model we've been learning actually does generalize to new data. Yes?
2 questions.
OK, so in this function, the fit function, you are giving to the model, so the first argument are the inputs. So in our case, we have 2 inputs, right? The text as a tensor and the questions as a tensor. And then you have the answers, which is the labels in our case. So you cannot input just words into Keras model because Keras model only take tensors. So much in the same way as we vectorize inputs and questions, we also vectorize answers. But there's one difference between the inputs and the answer, which is that the input is a sequence of words and the answer is just one single word. So the way we represent an answer is by one vector of the same size as the vocabulary. with just zeros and 1, 1 for the word that is the answer. Yes? Are you running on GPU or on CPU? Okay, so you're probably running on GPU, and it's slower than that. So that's possible because we are looking at a very, very small data set, 10,000 examples, and we are using a fairly small batch size of only 32. And what's happening in such situations is that the GPU is taking a lot of time to copy the data onto the GPU. And with Keras, it's going to do this operation of copying the data to the GPU every batch. So every 32 example, and that's a very tiny amount of data, is going to do this copying, which takes a while. And so the actual time you're spending running the network is very small because you're running on GPU, which is very fast. But in parallel to that, you are taking a while to copy the data. So that's why it ends up being slower than just running on CPU, which doesn't have this memory problem. So a trivial way to do it is to increase the batch size. Yes, of course. There are several ways. You can use, so Keras is using CNO in the background. So you can just look it up, how to run CNO on GPU and CPU. And there are several ways. So one way is with a command line. Another way is by editing your CNO preferences, which are stored in a dot file somewhere. So just look it up, and there are a few ways. Just look like CNO, how to run on CPU and GPU. You'll find an answer. Okay. Other questions? Yes. So we use 64 in several places. So here, it's the size of the dense vectors that are going to come out of the embedding. It's kind of arbitrary, You could set it to 128, you could set it to 32, or anything you want, really. So in general, in our case, we know it's a very small problem. It's a simple data set. There are not many words. The questions are not very complicated. So we know there is not a lot of complexity in this problem. So we can use a small embedding dimension. So we can use something like 32 or 64. If you were dealing with a larger problem, usually when embedding words, you want to use several dimensions of several hundreds. So for instance, word2vec is more commonly like 512 or even more. So it really depends on your problem. If you have a low complexity problem, it's fine to use small dimensionality. If you have a complex problem, like if you're trying to embed Wikipedia, for instance, you're probably going to want to have several hundred dimensions. What's that? What embedding does is very simply mapping a word to a vector, so an array of values. And these values are learned jointly to optimize this loss function. So it's very simple. You can interpret embedding as looking up a vector in a dictionary. Yes. Yes, that's right. Yes. Absolutely. So you are computing the output of the network on an example. At this output, you're comparing it to the actual answer. You're computing a loss value, and you are backpropagating this loss value through the entire network. And all the weights, so everything, the input embedding, question embedding, and so on, all the weights are optimized jointly with this one loss function. Yes?
training samples versus if you have 64. Because I see it as like, you know, the classic problem in learning is like if you have more features, typically more data.
So absolutely, that's right. It's more like the other way around. If you have lots of data and a very complex problem, then you definitely want to use higher embedding dimensions to be able to store all this information. So if you have lots of data, it means you have a lot of information to kind of embed into your network. So a network is kind of a sponge for information, right? And so if you have a lot of water, you want a bigger sponge. Okay. Yes?
Hang on.
So sequential is actually a topology element. It's a way to be able to tell Keras that you are making branches in your network, right? So that's your network. And sequential is just a way to say, oh, so we are going to have a sequence of 2 elements here, a sequence of 2 elements here, a sequence of 2 elements here, kind of thing. What are the options for what? You mean for embedding words? Sure. One very simple thing you can do is instead of embedding your sequence of words into dense vectors, you can just have a tensor that's all zeros and with ones for the index of the word you're trying to represent, right? So in that case, you would have a 3D tensor as input. The first dimension would be your different examples. The second dimension would be the time steps, so the words in the sequence. And the third dimension would be the size of vocabulary. And that third dimension would be all zeros and with 1, 1 for the index of the word you're trying to represent in this specific sentence at this specific time step. So that's one other option you could use. And you know, there are a few more. So there's really like no limits to what you can do, how you can approach a problem. I'm really just trying to show you kind of canonical patterns that are very frequently used and reused in natural language processing. So everybody was able to run this first example. Everybody understands what it does? Okay, no more questions, so I assume that's a yes. So let's look at our training. So right now, we are about 60% accuracy, but that's on the train examples. And we are only slightly above 50% accuracy on the text examples. That means we have started to overfit, which means that the model we are learning from our training examples does not generalize well to new examples anymore. So when you're starting to overfit like that, one thing you can do is add regularization to your network. So Howard told us about dropout. So we can try to add dropout to the network, see if that prevents overfitting. So the way you would do that, let's say after your embedding, input embedding, for instance, let's add a dropout layer. So dropout intensity of like maybe 0.2, which means 20% of the inputs are going to be randomly replaced with zeros. That's a way of introducing noise. So do we have dropout imported? Actually, we don't. So let's import dropout. It's located in keras.layers.core. All right, so we added one dropout layer after the first embedding. Maybe let's try to do the same with a question. Maybe train it, yeah, 50, that's not bad. I'm actually going to stop training that way. It's not very elegant, but bear with me. So let's run it with regularization, see if that prevents overfitting. So that's one thing you can try to make this model better. There are other things you can try. You can try, for instance, to replace the two LSTM units we have with other types of recurrent neural networks. So one thing that's available in Keras and that's quite popular is something called gated recurrent units, GRU. It tends to be faster than LSTM, but it's also less powerful. But since the problem is pretty simple, it might work well. So you can try that. So the way you would do it is first you make sure GRU is imported. So that's already the case here. And then you just replace LSTM with GRU. And the API for GRU is the same as LSTM. So that's basically all you need to replace. OK, so compilation always takes like 1 minute, at least on this small laptop. Yes? Yes, one thing you can do is output the configuration of the network, which is like a big dictionary containing the structure, like containing all the information you have to know about the network. And then we have some utilities for turning this configuration into a pretty diagram. But I didn't write these utilities and never use them, so I can't really tell you much about that. But yeah, there are ways to do it. You can look it up. More questions? Yes. I wouldn't say there's a rule of thumb. You really have to work with it a lot, develop some kind of intuition, I think. Because really, there's no rule because it really depends on, it's specific to every problem. Like every problem has to be solved, you know, in its own way. So what I recommend doing is just trying everything. So if you're not sure about the choice of an output size or an embedding dimension, just try a bunch of them. Try, you know, from 20 to 2,000 and see what it does. See what it does to compilation time. See what it does to runtime. See what it does to overfitting and so on. But generally, the patterns is that if you increase network dimension, you're going to see more overfitting because you have more entropy capacity in your network. So you're going to need appropriately as much data as you increase network capacity. If you increase network size, of course, it's going to run slower. It's going to compile slower. But also in some cases, if you find out that with your current network, you do not manage to overfit on your training data, even though you do not have any regularization. If you see this kind of pattern, it means that your network is too small, and you should try to increase the capacity. So a good neural network is a neural network that will overfit if you do not regularize with dropouts. So I think we do not have that much time left, so I suggest you try out these little improvements for yourself, and we're going to review memory networks, so which is a state-of-the-art architecture for solving the baby data set. So it's essentially the same. It's a type of recurrent neural network. So the authors of the memory networks paper describe it as a new kind of learning architecture, but what they're describing is like textbook recurrent neural networks, so which has been around for a very long time. But you know, they're Facebook people, so maybe that's why. No, I'm just kidding. If you work at Facebook, I'm sorry. For many reasons. So the one technical difference between this memory network and a classical recurrent network architecture like LSTM or GRU is the way the memory is handled. So this is what memory network look like. And basically, you have an input embedding, a question embedding, a second input embedding, and you're going to first compute a match between the first input embedding and the question embedding. And that match is basically kind of initial probability distribution over how much does each word in the initial input match the question. So how relevant is each word to answering the question, right? So that's already one mini way of solving the problem, right? And then you have this new embedding. We're not sure what it's here for, but maybe it serves a purpose, or maybe not. We'll have to try that. We sum this probability distribution with this new input. And because the output is a 3D tensor, you're going to want to reduce it to just 2D. So the way they do it in the Facebook paper is with a matrix multiplication, but you can also use a recurrent neural network to do the same. And then you end up with the same logistic regression. So how is this different from a recurrent neural network? Well, instead of the memory living in the state of the recurrent neural network, now the memory lives in the embeddings. So the embedding weights are how you store memory. So that's a new way to do things. Maybe the output will be interesting. So yeah, two things you should remember about this architecture, how to understand this architecture. First, memory lies now in the embeddings instead of the state of the network. And it implements a form of attention mechanism over past inputs. So what that means is that when you are computing the match between the input words and your question, you are implementing a form of attention mechanism that will pay more or less attention to different words in the inputs based on how relevant they are to the question, right? Okay, so let's dive into code. It's the third file called memmn. So same thing, we just exact same code as in the previous file, just extract the stories, vectorize the stories. And so here is the changing part. So this is just a straightforward implementation of this diagram. So as you can see, we start with two branches, we merge them. We have a third branch. We merge a third branch with the output of the merge of the first two branches. You add a recurrent neural network. You do logistic regression. So let's see how that looks like in Keras. So first branch, sequential embedding, okay. Second branch, so for the question, sequential embedding, okay, same thing, very simple. Then you merge the two. So you merge them with the dot mode, which takes the dot product between the output of this branch and the output of this branch. And you are specifying dot axis. So what does that mean? It means that you are summing the second axis of the first tensor with the second axis of the second tensor. So the second axis, by the way, is the embedding dimension. So you have three axes in your tensor. First axis is the example. Second axis is the time steps. And the third one is the embedding dimension. So once that's done, you instantiate the third branch, input embedding C. Here, so the same story, it's just an embedding layer. And then you will merge the two, and you will merge the two by summing them. So again, super straightforward in Keras. You just add a merge layer with the branch that's the dot of the first two branches, and the third branch, mod sum. So super simple, right? And then you want to reduce this to a 2D tensor and run logistic regression. So because the output of this is going to have this step, so first dimension is the examples, second dimension is the time steps, third dimension is the embedding dimension. And for the reduction, you want to reverse the two last dimensions. So you have the permute layer, and 2-1 means that the second axis is going to become the first axis. And axes are indexed from 0, by the way. So then you add the last branch, which is this reduction followed by logistic regression. So that's simply So for reduction, we use a recurrent neural network. You could also use just a matrix multiplication, which is even simpler. So you had some regularization already. You could remove it for a first run, but you're definitely going to need it at some point anyway. And then logistic regression is just a dense layer again, followed by a softmax. Then you tell the network you're going to optimize this loss function. So basically, the output of the network is going to be compared with the provided answer through this loss function, which should be provided to the network, and the backpropagation strategy. The strategy for updating the weight is going to be RMS prop in our case. So again, that's a very arbitrary choice. You could also use at dem, at a delta, at a grad, anything. Do not use SGD actually, because SGD tends to not work very well with recurrent neural networks. Okay, so then you train it. And again, because you have 3 branches in our case, the list of inputs is going to be 3 items. And then you have the output, so the labels. Batch size 32, you're going to run for 70 epochs. So 70 iterations over the entire data set. You want to display accuracy, and you want to display validation metrics on your validation data. Okay, so let's just try to run that. So again, compilation is going to take roughly 1 minute. So in the meantime, if you have any questions about memory networks. So this is supposed to be currently the best architecture for solving this problem. Published quite recently, I think last March or April. So this is really cutting edge stuff. This is the best thing you could do to answer reading comprehension questions. And it's only about 20 lines of Keras. And hopefully, they are fairly simple to understand, hopefully. With this setup, well, we're going to see, I think it's over 90%. It's somewhere between 90 and 100. So it basically solves the problem pretty well. And honestly, so Facebook reports 100. I don't think this network does 100, but if you just add more regularization or optimize certain layer size, you will definitely get to 100. So it solves the problem. So it's training faster, as you can see. I think it's also compiling a bit faster. So it's just training on my laptop. So what you want to do is implement a form of attention mechanism. So you have as input a series of words, and not all these words are relevant to answering the question. Maybe the input starts with some sentences about somebody doing something in the kitchen, but then the question is about a completely different place. So all that previous stuff might not be as relevant. So you want to weigh down that stuff. And what you do is that you compute a match between input words and the question. So that's what the dot product stands for. It's a match. Because in the previous model, you had 2 LSTM layers. In this case, you only have 1, and it's much smaller. And LSTM layers are basically what is taking all the computation in stack model. Like taking an embedding is essentially computationally free. Like, doesn't cost anything. It's just like a dictionary lookup, basically. A dot product is very fast. Softmax is very fast. Sum is very fast. And this is a much smaller recurrent unit, and you only have 1 instead of 2. So that's faster. Okay, so right now, where we're at, we are close to 100% accuracy for the training data. And for the validation data, we are getting close to 90%. As you can see, we are completely overfitting. Like, we are doing much better on the training data than the validation data, so that's bad. So solution, you just add regularization. So you add dropout layers. I would suggest adding a dropout layer after every embedding. We have 3 embeddings. Okay, so how much time do we have? I think it's been 1 hour, so it will be time to wrap up. So yeah, so this should get to over 90%. And if you want to get to 100, just take this code, add regularization, maybe optimize layer size here and there. And I will also give you one hint. So that's the things you can try. I will give you one hint. In the Facebook implementation, the second branch here is useless. So you can remove it. And you can just basically connect the softmax with a recurrent neural network or the matrix multiplication. And you will get essentially the same performance. So why did the Facebook people include this branch? Probably because they didn't really understand how the network was working, which is very common. So deep learning today is very similar to alchemy. At least the branches of deep learning that deal with very new models, like new architectures. Nobody really understands what's going on. There is no theory of deep learning that's guiding implementations. So people just try things. And if it works, and this thing works, then they're happy. And, but the fact is, try it for yourself. Try removing this branch. It doesn't actually serve much purpose. So that's funny, Facebook AI research. OK. So, well, we're not doing so well, actually. We are only reaching 88. So again, you could get 100% just increase network capacity, add regularization. A big problem, obviously, is regularization because you get to 100% of the training data, so you're completely overfitting. OK, that's it. So time for conclusions. So conclusions are that you can implement state-of-the-art research, things like memory networks, that's super advanced, in a few lines of Keras. And the implementation is pretty easy to understand. It's pretty easy to extend and improve, like for instance, adding regularization, changing parameters, replacing one layer from one type of recurrent network to another. That's super easy because the architecture is very modular. Facebook released a Torch 7 implementation of their memory network. And because it's Torch 7, it's actually very long and complicated and difficult to understand, difficult to extend. So that's, I think, a pretty strong argument for why you should be using Keras and not Torch if you're doing NLP research, because it's going to speed up your iteration speed, the speed at which you can try new ideas. If you have an idea, why not remove this branch? Why not add this other branch doing this other thing? That's like a couple lines of Keras. So you can do it in a few minutes, and then you can test it in like 5 minutes. So you can test something like 40 ideas a day, which is probably a lot more than what they're testing at the Facebook AI research. Okay, so so Keras has been pretty successful so far. You see it used a lot in academia, in the industry, also a bunch of startups are using it in production. You see it used a lot on Kaggle, which we heard about in the previous talk. So in particular, Keras has been used to win a number of competitions on Kaggle in the past few months. And it's not going to end there. OK. Any final questions?
The comment, the standard vector space for bag words and new stuff with whether it's here your approach formulation tells you care of time step here is pretty bad. Word action.
Absolutely.
And that's high.
This is no longer a bag of words. It's yeah, it's not a Markov model. It's quite different, but it is not bag of words because the one big thing with recurrent neural networks and memory networks is that the sequence, the order in the sequence of words you're inputting matters. You're not just taking the words and then averaging them. You are looking at a sequence, right? So that's a big difference. That's why it's a superior approach. More questions?
I was going to say one thing is check out the examples in the Keras repository. François has done a really good job of creating about 10 different examples, all very simple, about the CNN, RNN, kind of entire range of things. And yeah, they're very, very nice and very, very simple to understand.
So that's the examples. So this is an additional example that Stefan wrote. It learns to, it reads a string that's stating an addition. It learns to add the numbers. So that sounds pretty trivial. It's actually pretty tough to achieve. So you have the baby example. We just saw the first one. You have image classification examples, since you are 10. You have text generation example. For instance, this example is going to learn to generate some niche philosophy. It reads some niche books, and then it writes new niche books. If you didn't have enough niche in your library, you can generate new stuff. So yeah, lots of stuff, including some pretty cutting-edge stuff. So this is a reproduction of, like this is a couple lines reproducing a very recent cutting-edge deep learning paper by Jeff Hinton and Chollet from Google. So yeah, check it out.